Now, what if my integral is definite integral, like this, 0 to 1 tan inverse x dx. So here I need to go over everything using the indefinite form, if you like, until you come to the end, and then you plug the bounds, or you may plug them every step you have the bounds applicable. So let me start with the assumption that this is dv and this is u. So let u equal tan inverse x. The derivative of the tan inverse is, I have du equals 1 over 1 plus x squared dx, and therefore dv is dx, and from here v equals x. Put this back in the formula. The integral u dv equals uv minus the integral v du, and see what we get. I have uv x tan inverse x going from 0 to 1, where everything here is in radians. This is radian, and the 0 also is radian, but everything here is taken as radian as the value of x. Okay, so minus the integral of v du. V du gives me x divided by 1 plus x squared dx, and again this is running from 0 to 1. Notice that everything is on x here, so we keep the bounds, we don't change them. Okay, now this can be evaluated and we get the number of it. This one, it looks like it can be done by substitution. Once you can do it by substitution, you don't need to go do it by parts. Let's take it aside and call it number 2, and therefore with this labeled number 1, I'll take number 2 as the integral 0 to 1 x dx divided by 1 plus x squared, and then I go and use the substitution. This one I'm going to use substitution rule. Substitution rule says let 1 plus x squared, let u equals 1 plus x squared. So du is 2 x dx, or dx is du over 2x. So if I put this back in here, I get this integral equals the integral of, now x, I have here 2x in the denominator. Instead of dx, I can substitute 2x, so it will give me a half outside. But I mean, if we go and do what we used to do, you may multiply by 2, divide by 2, that is multiply by 1/2. So this becomes 2x, which matches the 2x dx, and then you get that as du. But let's substitute dx as du over 2x. So this is x. The dx now is du over 2x divided by 1 plus x squared is simply u. This x now removes this x, and I have a 2 spared out, and because this is now mixed with u and x, I keep the bounds in my hand, I don't use them. So this becomes simply 1/2 the integral of du over u. You may now transform the bounds and apply them here, or choose to keep them to the end. I'm keeping them to the end. Therefore, this is 1/2. The integral of du over u is ln u. And then I can bring this back immediately to the x form. So it becomes 1/2 ln 1 plus x squared. And now I may plug the bounds 0 to 1. When I do this, this gives me what? 1/2 ln 1 plus 1 is ln 2 minus ln 1 plus 0 is ln 1. Ln 1 is 0. So I have only ln 2 over 2. This is the integral number 2. So 2 is ln 2 over 2. Okay. Back to the original integral now, which is 1, which we agree that it is x tan inverse x from 0 to 1 minus this number 2. I can put this then the 1 as x tan inverse x from 0 to 1 minus the 2 here. I have its value ready, which is ln 2 over 2. Now this one I can substitute 1, so it becomes 1 tan inverse of 1 minus 0 tan inverse of 0, and then minus ln 2 over 2. Ln 0 is, tan inverse of 0 is 0. Tan inverse of 1 now, this is to be taken with 1 as radians, and therefore this gives me pi over 4. The angle with tan equals 1 is the pi over 4, and when you add this to this, you get the answer as 0.4385, and done.